Okay, you've got a homework assignment due on Tuesday, so what we need to do today is finish the StormCAD demo and go through some information related to stormwater detention so that you can complete that assignment. I've set the timer so that we can finish class early. It's starting now. Given myself an hour, so we'll make up for that time that I've kept you in the previous weeks. All right, so where we were last time when we were working through StormCAD is we had defined so far the pipe network. We had identified the invert elevations for the upstream and downstream junctions. We had defined the catchments, and let's just go back to the catchment table. Oh, I didn't save my work. Hold on, wait, what's this? Stopped working? I don't like that. All right, so I'm going to save this in case it does crash. All right, so let's go into the flex tables and just sort of review where we were. In the conduit table, we've identified, we gave labels to each of those pipes. Their start nodes and end nodes are defined according to the same figure that we had. We've got the inverts of the pipes set based on the inverts of the catch basins that they're connecting to. And the way that we know that is, see how it's in yellow here? That means that it's not user-defined. If we had ticked that box off, then it would allow us to user-define what the elevation of the pipe is. But right now, what it's doing is it's defining the conduits as having the same invert as the catch basins that they're connected to. Okay, the lengths, we did user-define those lengths. And then we can look and check the slope if we want. We haven't yet played around with the diameter. That's going to be the design component of what we're doing. We do know already what's the free flow capacity of these pipes. We know the capacity just based on the material, the diameter, and the slope. So Manning's equation is telling us the capacity. But what the system hasn't done yet is it hasn't sent a storm through our network. We haven't yet defined the IDF table, and so when we do, it's going to use the information for the catchments to generate flow rates and put flows through those pipes. And then what StormCAD will do is tell us what percent full those pipes are, and we'll go through the process of optimizing the sizes so that we minimize the diameter and save money. Okay, so the pipes are defined. If we can briefly take a look at the catch basin data, and we didn't bother defining the ground elevation because it's the invert elevation that is what set the pipe data. We could, if we want, we may get an error message about the ground elevation where we'll have to go in and edit that. I don't remember. It'll prompt us. But another important change what we made was we put the inlet location in SAG. So in the assignment, as you go through, if you get like one of those red error messages, the ones where it won't proceed, it won't calculate the flow getting into the pipe until you change it, most likely the error that you have to correct is identifying the inlet location being in the SAG. All right. And so if we go now into the catchment data, we had defined the area of the catchments, some runoff coefficients, and then the times of concentration based on the handout that we were given. And so how would you do this in the real world? Well, you'd have to go out to the site and maybe observe it when it's raining and actually try and track a particle as it flows from that furthest point of the watershed towards the outlet. Or you could use one of the methods like kinematic wave, NRCS, use one of the methods that can estimate the time of concentration based on the physical features like slope, rainfall intensity, roughness, and so on. Yeah?
Did you also take like a little thing of like food coloring?
Mm-hmm.
Like stand at the top and like see how long it takes to put together?
Absolutely, yeah. Tracer studies are done, and oftentimes they'll use tracers that you can't see unless you shine a special light on it. Yeah, like a tracer that is iridescent under a black light, something like that. Okay, so what we have to do now is we have to tell it about the storms. And we have to define an intensity, duration, frequency curve. So here under global storm events, we're going to create a storm event. All right. So we're going to do a user-defined IDF table. Hydro 35 is like data that's available for the whole country, and it can help you define an IDF table. But since we had a curve that we were using, let's do a new user-defined IDF table. So just again, where we were to get here, we're on the Home tab, click Storm Data, Global Storm Events, Global Storm Event, and then we're creating a new user-defined IDF table. And we're going to have to put in, or let's call this the add a return period, let's just call it the 5-year storm. And actually, we don't have multiple curves on the storm that we've got. So we have to call it something. So we'll just call it the 5-year storm. And now add range. Oh, no, we've got the 5-year one we're doing. Duration. All right, so the durations that we have data for, if we look on here, we've got, let's put in the 5, 10, 15, 20. So here's a 5-minute. And then we'll right-click. We'll add a new, well, let's do a range of durations. 5, we'll do 10, 15, 30, and 60. And it will interpolate 60. Okay. When we enter the data off of the curve, it'll interpolate everything in between. So if we go to the curve, the 5-year, it looks like that's about 5.35. 5.35 for the 5-minute duration, inches per hour. We got to make sure that the units match up, and they do. Our figure that we're working with is inches per hour, and so is what we're typing in here. Here, add duration, or that would just be to do one at a time, but if you add range, then you can type it in, and every time you press enter, it'll generate a new one. So it's add/remove durations. All right, so the 10-minute, it looks like that's about 4.15, 15-minute, 3.2, 30-minute, 2.3, and 60-minute looks like about 1.651. All right, I'm just kidding. It's 1.65. So we've got an IDF table there, and you'll notice now under the drop-down box, previously it wasn't there, but now we have this storm that we've defined, what we're calling the 5-year storm. Okay, and so now if we click compute, it knows what storm to use because we told it to use that everywhere, globally, it's going to use the 5-year storm that we defined. We connected the dots from watershed to inlets, and I think we've given it everything we need. The only unknown is in my mind is if we're going to have to define those ground elevations, if that's a critical error, if it's just going to warn us about that. So let's click compute and see what we get. Yeah, all right. So the invert elevation is higher than the rim elevation. Inverts must be lower than the rim elevations. All right, so I think we need to go into the catch basin table and define those rim elevations. So let's go to the catch basin, and let's just put the ground elevation at 800 for everything. And that way we'll save a lot of time. If you do a global edit, it's going to be really deep according to the program, but it's not going to change the hydraulics. So everything is 800. So now The ground is really high, the rim is really high, but the only thing in this catch basin table that we were using for the design was the invert elevations because that sets the pipe slope. All right, so now if we recompute that, hopefully that error message will be gone. We've got some warnings here though. It's saying, certain of the pipes, the conduit discharge is above the design discharge. And we'd expect that because we haven't actually done any pipe sizing optimization yet. So a lot of these warning messages are about the pipe's not big enough. And we can fix those when we size the pipe. Another one of these warnings here is about our outfall pipe, that the slope is too big. And it's like kind of an impossible slope. You can't have in such a short pipe such a big vertical difference. But remember, we just need some place for the water to exit the network. And so this outfall pipe, we're not really sizing anyway. Okay, so really the way to look at what happened is to go into the conduit table. Because what we're trying to do in the conduit table is find out on a percentage basis where's the flow greater than the capacity. So if you look at these percentages, only a handful of pipes are actually adequately sized so far. Anytime it's less than 100%, then that tells you it's okay. Actually, it might be oversized. In the case of this 37%, so that's saying that we're only 37% full. So if this so-called 5-year storm that we just put the data in for, if that's our design storm and we want all of this water to be captured and conveyed by the network, but anything more than that should cause our system to fail, then that means actually we need to make that conduit a little bit smaller than it is right now. So what we ought to do maybe is, I don't know if it'll allow us to sort by, okay, sort from smallest to largest, and that'll help us to pick some new sizes. So let's take this 12-inch just to see what happens, take it down to an 8-inch, all right? And that's going to tell us that already it's updated the capacity, and based on the previous analysis, what the flow rate was coming in, 8's too small. So we could make that one 10-inch, and we're good. We'll try 10-inch for this one. That's good. Well, what about 8? 8's not going to do it. So it looks like 10 is probably going to be the smallest acceptable pipe diameter everywhere in our network, and that pipe G that I just optimized, 10 isn't enough, so we'll have to leave it at 12. Okay, looking at pipe A, where it's 12 right now, but then the flow relative to the capacity, we're over 100%, so that's not good. So let's make that 14. 14-inch will do it. See if 14 is not big enough for pipe I, so we have to take that to 16. We'll try 16 for this next one. It works. 16 isn't good enough for pipe C, so we'll switch to 18. Still not good enough. There's a 20-inch pipe. That'll do it. We've got a lot of overcapacity for this pipe E, so we'll just jump straight to 24. That does it. What about 22? No. So 24. Will 24 do it for pipe H? Not quite. We've got to make that 28. Nope. 30. This is getting to be a really big storm sewer here. There may not be a commercially available 34-inch pipe. We'd have to check with our suppliers to see, but I think probably 36-inch would be the next largest available pipe. And then finally, pipe J is going to have to be absolutely enormous. Even at 36, we're just barely over capacity 102. So the next pipe size could be 40-inch. All right, so that's the optimization. And of course, there are other pipe sections available. You know, there are some pretty obscure pipe sections available that will be pretty uncommon to see in the municipal network, but there may be some historical sewers that have pipe arches and like the sewers of Paris, that sort of thing. So any questions that I can demonstrate again how we did a certain thing? You know, if we run this network again, if we compute, we're going to see a lot fewer error messages this time. And most of the ones we have are related to maximum cover. because what we're saying is, we kind of placed the pipes without looking at the ground elevation too much. The maximum cover, that's saying you wouldn't have the pipe like 100 feet underground, because remember where we set the ground elevation to 800, there's too much cover on most of these pipes. But none of the rest of these error messages are related to the capacity of the pipe. It's just cover warnings. There is one catchment maybe we could look at. Catchment 6-1 is time of concentration. And I think that's because this catchment, 6.1, since that was just connected to our outfall pipe, I think I gave it an area of 0. So if it has 0 area and it's got 0 time of concentration, then let's see, where was the time of concentration? 0 minutes. So it's kind of complaining that our IDF table had a minimum of 5 minutes. That was the shortest time on our IDF table, and so it doesn't know what time of concentration would assign to that. Really, what I ought to do is just delete that catchment altogether because it wasn't a part of the network. The last pipe that I wanted to size was this pipe J. And so water gets into pipe J from the upstream pipe H, from the junction at 5.1, and the upstream pipe I. So now if I execute the model again, at least that warning about the time of concentration is gone. The rest of these, I think, are just not warning messages that are concern to us, because we were really just going through the process of demonstrating how to size the pipes. But just to reiterate, it's in the conduit flex table that you can look and see if things are correctly sized. And remember the way of adding annotation, that's the same as it was in water gems. Like if you wanted to right-click on conduit and have a new annotation, then you can have diameter. So let's see if we can annotate the diameter of these pipes. So diameter and prefix D equals. It's going to have the units with the suffix %U. And we might have to play around with the offsets to get it in the right spot. Maybe if we do an X offset of 3 feet. Oh, that's no good. There we go. It's the Y offset. We're getting it kind of out of the way. And of course, you can drag those labels around a little bit to get them in the right spot. So the annotations, maybe you want to annotate for the catchment like the areas. So a new annotation label where we have the area. We'll have area equals, and we'll do some offset there. So we've got areas defined. Maybe we'd want to put in the C values, so we can do a new annotation label for the runoff coefficient rational. C equals, and we'd maybe do that below, so -4. Okay, we threw on some C values there. So the network's starting to make sense, and you can build reports that gives you all of the data, like the sizing of pipes and so on. Any questions on the illustration for StormCAD before we move on? All right. If you do have questions, feel free to stop by during my office hours or send me an email. It's just occurring to me for the first time to offer this suggestion. I announced it in my previous class, but if you have like a question on the homework over the weekend, it's helpful if you take a picture of the question you're asking me about. Because I may be like out in the woods or up in mineral wells at a cross-country meet or something, and if you ask me a question like, what C value should we use for number 8? I don't know what number 8 is, and I don't remember what that problem is, and so to answer that question, I have to wait till I can get into the office and grab my textbook. But if you send me a picture of the question you're working on and the assignment you've done so far, then even if I'm out in the middle of nowhere, I can kind of get a basis for what question you're asking about, and it may enable me to respond more quickly in situations where I didn't necessarily take the textbook with me where I'm at. So I'll do my best to respond as quickly as possible if you have an email question, and you can kind of meet me halfway on that if you give me a lot of information about which problem you're actually working on. All right, so we finished the StormCAD demo. Let's talk a little bit about stormwater detention. Remember that urbanization has the effect of making the peak higher and come sooner than it would have in the natural state of the land. And the reason for that, the difference between before urbanization and after urbanization, is that by adding impermeable surfaces inside of the watershed, we're speeding up the flow of the water over the surface of the land. Because when water is flowing over like a grassy surface or flowing over forest litter, there's a lot higher roughness value than water flowing over smooth pavement. And so, number one, we changed how quickly the water is able to move over the surface, and especially when we add channels in. If you think about a gutter or a pipe, water is able to flow much more efficiently through an engineered conduit than it can through a natural channel. And then the other half of that equation is that in addition to speeding up water, you've also, through urbanization, you've increased the amount of impermeable surfaces. And so a gravelly area or a vegetated field in the past would have a relatively low C value, which means a lot of water is infiltrating. But when you urbanize, the march is inevitably to put in roofs, asphalt for roadways, parking lots, and sidewalks or concrete, and none of that infiltrates water efficiently. So the runoff hydrograph is the peak is sooner and higher. This figure is showing two things. The hydrograph, which I've just shown you, above that, this is called a hyetograph, a rainfall hyetograph. And so the hyetograph, this one, is breaking the rainfall up into distinct periods. Rather than measuring it continuously, they're reporting an average during a certain period. And so it may be that this storm was 3 hours long, and during the first hour of the storm there was a certain intensity, and then the rainfall intensity went up for another hour, and then the rainfall intensity went down again. What this rainfall hyetograph is showing is what fraction of the rainfall back in the olden days used to infiltrate. And so all of the water underneath this top line, so before urbanization, all of that water infiltrated. And I'm going to write a conceptual formula on the whiteboard here, and it is rainfall excess equals rainfall minus infiltration. Another word for rainfall excess is runoff. Okay, so conceptually what this means is that before urbanization we had lots of infiltration for the same amount of rainfall, assuming that stays constant. If you had more infiltration back in the olden days before we paved over everything, then that meant during those olden days there wasn't as much rainfall excess as there is now. So developments like, you know, that Amazon customer service center, that used to be natural land. You put a big warehouse and loads of parking up on that hill, then the people downstream of that hill are going to see more flooding than they used to. So if you live out in the countryside and it just somehow seems like the creeks are higher than they used to be, it could be that there's development in your watershed. And the reason why is there's less infiltration, and for the same amount of rainfall, then there's going to be more rainfall excess. So what this figure is showing is that after urbanization, now there's less of the area under that curve devoted to infiltration, so more of it is going to be the rainfall excess. Okay, so what we're trying to do in stormwater control is mitigate those effects. And there's a variety of ways of doing it. We just have to think a little bit differently, and the goal is always to try and delay water's arrival to its ultimate outfall. And by outfall, I mean maybe the water's going to a creek, maybe it's going to the Ohio River or to a lake. We just always want to slow water down when there's a storm, and as much as possible encourage infiltration. So what this best management practice is showing is a vegetated filter strip. So what that is essentially is just a grassy area by the side of the road where water is forced to flow over the surface before it gets into the ditch. They could have put a ditch or a curb immediately adjacent to the roadway, but by doing that, you're immediately channelizing the runoff. Instead, it's better to have a little bit of sheet flow before you go to channelized flow, because channelized flow is fast. When you've got a depth of water, it can move with less resistance through that channel than if it's flowing as a sheet. So you just think, what kinds of flows are slow, sheet flow? What's going to improve infiltration? Vegetation. And so that's the idea of a filter strip. And this is showing it next to a roadway. There are places where they do the same thing in a parking lot, where just putting in patches of grass in a spot where you know peak cars aren't going to be parking can have an enormously positive impact. And also it improves the water quality as well. This figure is showing if you have a stream and you have a filter strip before that stream, it's called a filter strip because the water quality is improved if the type of water that comes off of roadways, it has oils, it can have some of the hydrocarbons from fuel. Salt is applied to roads and sand for grit to help people get traction. And none of those things have a positive effect in the aquatic ecosystem. All those things have negative effects. So if you have that water flow over grass, then the grass can extract some of those pollutants and the sediments can settle down into the grass. And so it's better to have the pollutants hit the grass than it is to hit the stream, because the organisms that are in the stream are more sensitive. All right, here's another illustration, and this is something that's been pretty hot in Huntington for the last 5 or 6 years, is trying to get people to disconnect their roof drains. And I previously already told you about our combined sewers here in Huntington and how about half of the network has both wastewater and stormwater running through the pipes. And when it rains, that stormwater makes its way into the streams and pushes the wastewater along with it. And so if you disconnect the, what have I done? If you disconnect the roof drains, then you're going to be reducing the amount of water that gets into the combined sewer. And if people are worried about flooding their yard, you're not supposed to put runoff water next to your foundation because it can damage the foundation as well. But all it takes is a little bit of an extension on the drain to get the water away from the house, and things can be completely fine. There's going to be sheet flow, there's going to be more infiltration. Sometimes they take this disconnection to the next level, and the next level approach is if you enhance the infiltration capacity of the soil. And so if you kind of extract a clay soil and you put in sand or otherwise amend the soil with little plants, then that can be another way of disconnecting your roof drain, but then also encouraging even more infiltration than there ordinarily would have been. You can see that there's a bit of like a dam edge around here. So they're kind of making a temporary pond when it rains in their yard. So that could be kind of nice, a little ecosystem in your side yard. Here's showing that filter strip idea in a parking lot. They call it bioretention. If you are selective in the types of plants that you put in, if you make sure that they're native plants and plants that can extract a lot of water from the ground and try and increase the amount of evapotranspiration, then that's a favorable thing. So bioretention is another BMP. That acronym BMP means Best Management Practice. And it's a term used in a lot of different industries, but in terms of stormwater, these BMPs are different ways to promote infiltration and delay runoff. So here's another one. Trying to make it so that concrete absorbs more water than it ordinarily would. And so one approach is to use concrete pavers and packing gravel in, where it used to just be a continuously impervious surface. Now you've got a little bit of impervious surface with the paver, like this might be a cinder block that then you reinforce with gravel. And so there's going to be better infiltration there than there would just be for pure concrete. And speaking of concrete, let's see if this YouTube video is still up. It shows some porous concrete. Because if you think about it, if this isn't well drained, if the subgrade beneath the concrete isn't well drained, if there's water backing up and it freezes, it's just going to break that apart, no problem. And so I think the key to good porous concrete is to have some slope to it and to have big pieces of gravel, like a thick gravel layer underneath so that the water can really move through and get out before it freezes. Yeah? Yeah, that the whole town of Huntington would benefit. But it doesn't have the longevity, the proven longevity that ordinary concrete does. And we have enough trouble just with ordinary materials. To switch to something more fancy would be a challenge. But I think it's a great application for like a university. This was at the University of New Hampshire. And so universities generally have a little bit better maintenance than cities do because you got to keep the university nice or people won't come here. You got to make it like tourable condition. So that's an illustration of like different ways to just think of paving in a new way. Okay, a grass swale, that's a fancy name for putting grass in the ditch. So why would a grassy ditch be better when it comes to fighting the effects of urbanization? Why is a grassy ditch better than just a dirt ditch? Slower. Exactly, yeah. It's because this grass sticking up into the flow has a higher end value, so the velocities are going to be decreased. Also, there's the advantage of the grass is going to keep the sediment in place. And so scour and erosion is a real problem in streams. And so if you can get grass to grow because you've got enough sun, in a lot of places here this wouldn't work because you've got a tree canopy over the ditch, and so there's just not enough sunlight for the grass to grow. But there are spots where it will, and where it does, it helps to prevent the channel from being damaged during big peak storms. Okay, here just promoting new ways of having additional infiltration. What this is showing is this is a pond, a local pond in a commercial development where the runoff from this parking lot is going towards the pond, and what they've done is they've dug out the center of the pond and amended the soil there. Instead of just having it be the whatever soil it was initially, they've put in gravel and where the water can seep down to the subsurface more easily. Regenerative stormwater conveyance channel. Instead of having a straight line that the water just flows downhill, by having a series of pools, what happens during a storm is if these pools were dry to begin with, the first pool has to fill and overflow to the second pool before any of the water makes it downstream. And if you think our whole objective here is to delay how quickly the water can move from one spot to another, this was a relatively steep channel to begin with, and so the water would have been very shallow and moving quickly over that surface. There's probably a good chance of scour of whatever the material was. And so the idea here is that you build up a series of smaller pools, each of which have to fill before there's any movement towards the creek. So that really reduces the damage to the surface for steep slopes. Rainwater harvesting is becoming kind of common. Especially in Australia, they do a really good job of capturing rainwater off of roofs. Here in Huntington, they've done that. Do you know where Latas is on like 4th Avenue? Or maybe it's where it used to be. I think it might be closed now. But they have a big tank like this where they were capturing the stormwater off of their roof. And the plan there was to use the stormwater for watering the flowers in Huntington. Yeah.
How was it illegal to take the water that came onto the roof and recycle it?
Nope, it's not. Nope. And in fact, here in Huntington, they were buying rain barrels for people for a while. I don't know if that program's still active, but the city of Huntington was paying for people to disconnect and to attach rain barrels. If it's illegal, let them arrest you. Good thing to go to jail for. All right. Here in the engineering building, we've got a vegetated roof, and so you've seen those if you've peeked out the door. I don't know why they've got those doors locked. It would be better if it wasn't locked. We have barbecues up there and smoke and stuff, you know. All right, we got to zip through these, otherwise we're not going to get to the stormwater sizing. Filtration practices just acknowledges the fact that this is a gasoline station here, right? This is obviously a filling station, and these sorts of places are notorious for even just a little bit of spill onto the ground for each car is going to put a serious amount of hydrocarbons, and the pollutants in that, like benzene, toluene, xylene, BTEX, those pollutants are carcinogens. And if they get into the water, that can infiltrate down into the groundwater. It can have effect on the fish and the birds and the insects that live in streams. And so finding ways to capture especially polluted water like that at a filling station is important. So it may be something like a passive filtration, where just by gravity you're separating oils from the top, sediments from the bottom, and maybe a separate pond where the organics can vaporize out before they get into a stream. A constructed wetland is becoming quite popular because constructed wetlands have a way of improving the water quality. Constructed wetlands are like a stormwater pond that's meant to always have some water in it. We'll look at some sketches, some hydraulic sketches of the types of fittings you'd need for an extended aeration basin versus a constructed wetland and so on. But here, biological uptake of nutrients is really important because sometimes the pollutants aren't necessarily just limited to heavy metals and sediment and organics, but sometimes just nutrients like nitrogen and phosphorus, which a farmer may be adding to a field in one location. So it can be beneficial for agriculture because it stimulates the growth of beneficial plants in a crop area. But when those pollutants run off and get into a stream, then they can have really harmful effects. And there's been a lot of talk lately of red tide in the Gulf Coast. And if you've heard about that, what it is it's when nutrients get into the ocean, it stimulates the growth of bacteria and algae. And those bacteria and algae, they consume not only just the nutrients in the water, but they also consume the oxygen. And so there will be these what are called dead zones in the ocean where there's no dissolved oxygen, and it causes fish kill, and it can be pretty nasty, the breakdown of organic constituents in the absence of oxygen, the anaerobic consumption of organic material can form like hydrogen sulfide, which is corrosive, and we've talked about how it's dangerous for humans when it's in pipes and in an enclosed environment. So constructed wetlands has the advantage of nutrient removal because what you're doing is you're stimulating the growth of plants like cattails and trying to have aquatic weeds grow. And sometimes you may need to harvest those aquatic weeds in the constructed wetlands and dispose of them in a landfill. But it's a lot easier to do that than to allow the polluted water to make its way into a protected stream. Okay, detention ponds is the bulk of what we're going to be talking about for the rest of the lecture today. And a dry extended detention pond is dry because it doesn't have water in it on a continuous basis, in contrast to a constructed wetland. A constructed wetland is always meant to have water, but a dry extended detention pond is only going to receive and have stormwater during the stormwater event itself. The wet pond is a little bit more like a constructed wetland. All right, so remember, here's our hydrograph and hyetograph. A hydrograph is a figure depicting runoff. A hyetograph is a figure depicting rainfall. Stormwater ponds exist to mitigate the effects of sooner rainwater runoff and more of it. So the problem we're trying to solve is that there's more volume of runoff and it's coming faster and the pollutants that can occur in an urbanized environment. So we're trying to make the after look more like the hydrograph was before urbanization. There are a couple approaches to doing that. You can try and prevent the water from getting into streams in the first place, and that's often called source control. So source control may be regulations like was levied on Cookout, where they had to put in that special pervious pavement because the city doesn't want the runoff from their restaurant getting onto Fifth Avenue. And so that would be an example of local disposal. Another example of local disposal would be in a shopping development, how they have to set some of the land aside for a pond. And so if you've ever been to Target before, and as you're driving up to Target on the left side of the road, there's a really big, significant stormwater pond on the left side there. It's super deep, and they've got a chain link fence around it because when it fills, it's going to be very deep, and they, I guess, don't want kids getting in there splashing around. So those are illustrations of trying to hold on to the water and delay it as close to the source as possible. Downstream control is talking about measures where the water has already come to a point of concentration, and now you have to build a much larger stormwater detention facility. And so that big cavern in Japan, the concrete vault that they had, that's an illustration of downstream control. An extended detention basin is one that is intended to have water just on a temporary basis. And so the perforated riser is, the holes are at the bottom of the pipe. So water comes in, and if the inflow to the pond is greater than the outlet flow, then the pond is going to start to fill. But it's not until the water gets to the spillway that the water can go through the outlet in kind of an unregulated fashion. A little bit can trickle in through these perforated risers, and some is going to be coming through the outlet. But the purpose of this primary spillway is it would be basically a vertical pipe, and the water can enter this pipe without restriction once it gets to the maximum storage level. The purpose of a circular baffle around the primary spillway is just to keep grease and sticks and other debris from getting into the outlet pipe. Typically, an extended detention basin would be used for situations where you expect the pond to have water maybe about a day or perhaps a little bit longer. And the environmental benefit it has is it's settling particulate pollutants. But the problem is that there can be a risk for mosquito breeding if the area stays moist for too long. In contrast to the extended detention basin, look at where the perforated riser is. Now, in the case of a retention pond, the perforations are at the top of the pipe. So no water is going to be leaking out during the storm. It's only when the water level gets above those perforations that the outflow will begin. And so a typical residence time, the average time the water particle spends in the pond would be 2 to 4 weeks. And that's selected because what we're hoping for is a much longer treatment time for the nutrients to be removed by whatever plants are growing inside of there. And the process of photosynthesis is extracting some of the pollutants and causing plant mass to form. And a part of that plant mass is the phosphorus and the nitrogen that was dissolved in the water. So this has the advantage of a biochemical removal of dissolved nutrients. But the issue here is that this extended detention basin is dry most of the time. And so it's much easier to maintain. You don't have to drain it to maintain it. You just have to occasionally, if there is a lot of sediment at the bottom, you could send a crew in there with a backhoe or some sort of shovel and bucket and remove the sediments. But in the case of the retention pond, it's going to be a much larger effort to completely drain the pond, and then you've got probably like a benthic muck, like an anaerobic breakdown of organic material at the bottom of the pond since it's always submerged. So that can be a little bit nasty. The risk of anoxic conditions means that there may not be dissolved oxygen at the bottom of the pond, and so there is the possibility of hydrogen sulfide formation, and kind of worms and insects that form in a low oxygen environment are generally considered to be kind of a little bit undesirable. So how big should the pond be? This figure is showing that the pond is storing the difference between the inflow hydrograph and the outflow hydrograph. So look at what we've got is over time the discharge of the pipe that's feeding the pond, which is the inflow curve, and then the outflow curve. So the pond is going to store the difference between the two. So its accumulation is in minus out. So this V sub S is the accumulation inside the pond. So ideally what we'll have is an inflow hydrograph at high resolution, at least hourly increments. And the more frequently, then it's better, because what we're doing kind of is a numerical integration. We'll calculate the volume into the pond during some time increment. We'll calculate the accumulated volume up to that point, and then we're going to find out how high is the pond, because it's the pond depth that dictates the flow out. In most cases, what these ponds have is just an orifice, and so it's going to be the orifice equation that says the flow rate out from the pond. And then we do this hour by hour. We see how much came in, how much flowed out, what was the depth that dictated the flow rate out, and so on. Okay, so here's an illustration. We're going to go through and with Excel size a pond and find out what's going on here. Just for simplicity, let's assume that this detention pond has square edges. Now, that's not realistic, but the geometry is a little bit simpler for this first exposure to the method. More realistically, what we'd have kind of like a trapezoidal shape of a pond. It's sloped at the edges instead of being straight up and down at the edges. But just for simplicity, let's say we've got water coming in. Here's our inflow hydrograph in terms of cubic meters per second over time. And what we want to do is find out what is the peak flow rate out of the pond for a certain size pipe. We've got a 250 millimeter pipe, and we're using the orifice equation. V is the square root of 2GH. And what I hope you remember from fluid mechanics is in the orifice equation, if we have an outlet, we measure from the center of the orifice, and H is the distance from the water level to the center of the outlet. And then that is what would tell us the velocity of the flow outward, the orifice equation. All right, so let's start up Excel here. I've got 11 minutes till my alarm goes off. Let's do this. All right. So we'll start with the blank workbook, and the pond characteristics here is it's a 65 meter by 65 meter. That's the top view of the pond. So 65 by 65, 0.25 meter diameter pipe. So the columns we're going to put in, let's go a couple of rows down, and then we're going to put in a column that's time, and then the inflow in terms of cubic meters per second. All right, the volume in cubic meters, and the accumulated volume in cubic meters. All right, the depth at this point in time, the H value, which is going to be slightly different than the depth because of the orifice, the outflow in terms of cubic meters per second, and then we'll have a column representing the volume out in terms of cubic meters. All right, let's see if we can figure this out. So our time starts at 0, goes 1, 2, and so on. We may need 23 hours to see what's going on here. Let's look at a 23-hour cycle. Our hydrograph that we were given is that at 0 time, the flow in is 0, but then we've got 0.3 cubic meters per second, then it goes to 0.67, then 0.81, 0.67, and 0.22. Let's just make sure, does that match the given data? Yeah. All right. Now up here at the top, let's just put some of the data that we know here, like the pond area in terms of square meters. The pond area, that pond was 65 by 65, so I'm going to do equals 65 times 65. Got the pond area. The outlet pipe diameter in terms of meters was, that was a 0.25 meter diameter pipe. And let's calculate the pipe area from that. Okay, we're doing pi times d squared divided by 4. Okay, it gives us the pipe area. And the C sub d is the coefficient of discharge. That's related to like energy losses as the water approaches that pipe outlet and goes through that pipe. And the C sub d that was given in the example sketch, it said it's 0.59. So we're going to use that when we calculate the outflow. Any questions so far on what we've got on screen? All right. So the volume in, V equals Q times the time. So it's equal to inflow times the number of seconds in an hour, 3,600. So there's no volume in yet, but if I double-click that formula and have it go down through the rest of the spreadsheet, for instance, during the hour 1, if the flow is 0.3 cubic meters per second, and we multiply that by 3,600 seconds, then that tells us there are 1080 cubic meters that flowed into the reservoir during that time. Okay, so our accumulated volume, it's 0 at first, so just 0 in time 1. At this next time, it's just what's come in so far, because there hasn't been any outflow yet in the first hour. So we'll just say it's 1080 to begin with. We may have to come back to that column later, though. We can't necessarily carry it all the way through. All right, so what is now the depth and the H? All of that's 0 when the flow in was 0. So it's hour 1 where things get a little more interesting. So the depth, if our accumulated volume is 1080, the depth is the volume divided by the pond area. Okay, so if there's 1080 cubic meters in that pond, and the pond has a known area of 4225 square meters, then the depth is just going to be 0.255 meters. Any questions about that or anything else so far? Here's our pond, and here's the outlet. So if this is the depth is from the bottom of the pond to the water surface. Here's H. H is from the center of the pipe to the water surface. And so what we have to do for H is we have to say it's equal to the depth minus the pipe diameter divided by 2. So we just have to subtract out half the pipe diameter from the depth. Okay, outflow. Remember, for the orifice equation, Q equals C sub D times the area of the pipe times the square root of 2GH. So this is the formula we're using for outflow. So it's equal to the outlet pipe area times the C sub D times the square root, SQRT, of 2 times G, 9.81, times H, which was this column F value. Mm-hmm. So we've translated this orifice equation, C sub D, area of the pipe, square root of 2GH. That's our outflow. And so if that's the flow rate out, then the volume out is the flow rate out times 3,600. I'm going to reduce the number of digits that are shown to something slightly less ridiculous. All right. Okay, so then, hour 2, accumulated volume. This is where we have to be a little bit careful here. So the total amount of water in the pond is the previous amount of water that there was, plus the new water that came in, minus the water that flowed out during the last time period. So this is why it's good to use small time steps. Is the smaller the time steps are, the better this numerical integration works. But we're using the volume out during the previous time step. And so it's not perfect, but it's good enough. Does everybody get this? Accumulated volume? Let me do it again just to make sure. So what we're saying is, in the second hour, the accumulated volume is the previous accumulated volume. How much water? The accumulated volume is how much water is in the pond now. Okay, so the amount of water in the pond now is how much water was in the pond last hour plus whatever flowed in minus the volume that flowed out. And the best we know about the flow out was during the previous hour. That's our best estimate. So that's why we use the previous hour. Okay, so now we've got accumulated volume, and we can drag the rest of these formulas down. Everything else is just going to kind of be the same approach as the previous time. Depth is based on the volume. H is based on the depth minus half the pipe diameter. Outflow is a function of the orifice equation. Volume out, everything we can just drag down through the entire 23-hour time period. And what we see, hopefully, is that the water depth gets deeper and deeper, but then the pond starts to drain because the storm stops. At hour 5, there's no more water coming in. So now what we've got is it's draining. I've got 60 seconds left before this alarm goes off. So what I'm going to show you is how we would turn this analysis into design. What if there was a regulation that said, well, that's all well and good, but the water shouldn't be any deeper than 1.5 meters. So what would we have to do to get it so that the depth never goes higher than 1.5 meters? Okay, good. That would be one way. And would we want the pipe diameter to be smaller or bigger? If we want to limit the depth to 1.5 meters, would we want the outlet pipe to be bigger or smaller? You want to let more water out or let less water out? More. So one approach would be make the pipe bigger. Okay, let's do that. Let me change this outlet pipe from 0.25, let me change it to 0.5 and see what the maximum depth right now. I'm going to do this max function. 2, 1, 0. It's not a very loud alarm. All right, I'm out of time. So let's just do it 0.5, yes. Now the depth is smaller. The other approach would be make the pond bigger, increase the pond area. All right, so we're done. I'm going to send you a short example by email that just addresses other ways to calculate pond sizing. This is the real way with a spreadsheet, but there are kind of like some empirical back-of-the-envelope methods that have been developed And there's a very simple example in the notes that I'll send you a PDF of. So let's just revisit these announcements one last time before we finish. Your assignment is due on Tuesday. I'm going to take a look at that and make sure that we've covered everything that you need to know to solve that assignment, but I kind of think we're most of the way there, so I'm not going to change the deadline of the assignment, but you will hear from me with this one more example. That's it for today. I've repaid you that stolen time in full now, so I can start stealing it from you again next week. All right, have a good one.